Okay.
Okay,
So then all.
so any questions on the labs? Now, let me point out one thing that notoriously goes south on this lab. So here's your graph, here's your elongation, okay? And you got some data points, kind of like this, I'm guessing. And you're gonna come in here, you're gonna draw your best fit line. Okay, come split the difference, there's your line. Cool. Now, here's what's most important in terms of how all this deal is going to play out. On this front page, up here in the top left corner, where you've got, or it's bottom right, excuse me, where you've got a little asterisk. That's the elongation that corresponds with that 1.5 kilograms. So whatever that elongation is, this is what you have to do. Usually that's around 0.25, 0.27, something like that. So come over here and find out, make a mark wherever that elongation is at the maximum elongation, wherever that asterisk is. Find that point, and then you're going to draw a line straight up to where it intersects this line of best fit. Okay? So find your maximum elongation. Go here, go straight up. Figure out where it crosses the line of best fit. So one of the things that, and this is what you're going to do in all these calculations, then you're going to write that x and y coordinate here, however many centimeters and however many newtons that is. Now, you can only use the weight that corresponds with that maximum elongation if it's actually that point, okay? But if that happens to be your actual data point for that maximum elongation, you can use it. Odds are it's probably not. So then you're going to come up here, find this point, go across, find out however many newtons corresponds with that point, and write that down there. Okay? It might be the actual amount of weight that corresponds with that. If it does, great. But odds are, most of the time, it's not. Okay? Everybody cool with that? Now, when you get to question number 9, it says, using the average force. Don't make this difficult, okay? Here's the increasing amount of force. You're starting at 0, you're ending up with whatever value this is. How are you going to find the average force between this point and that point? Add them together, divide by 2. So basically, you're saying on average, you're applying this amount of force. Okay? So take 0, add it to whatever force corresponds with that maximum elongation, divide by 2, multiply that by this length. Basically, all you're doing is finding the area of that triangle again. Okay? Which is the exact same thing. Everybody cool? Anything else you want me to go over? Michael?
Number 12.
Okay. So here, let's talk about number 12. And you have to realize what that 10 meters is. Okay? So here's your ramp. So the 10 meters is that vertical distance. The 10 meters is not the length of the ramp. Okay? It is not the length of the ramp. This is what's 10 meters. You don't know what the length of the ramp is, and you don't know what that angle is. But all you know is that this person, here's the wheelchair, okay, and they're going to move up like this. Now, to give you some perspective, this is actually pretty tall, because 10 meters, this ceiling is about 2.5, okay? So you're actually moving this person up quite a ways, like a 4-story building. So there's 2 ways that you can do a calculation on an inclined plane. And I don't care how you do this. You either take force parallel times the length of the ramp. Okay, but you can't do that because you don't know what the length of the ramp is, nor do you know the angle, so you can't find the force parallel. So you can't do this calculation if you try, because you can't find the force parallel. You can't do it. So the other thing that you can do is you can multiply the gravitational force that you have times however high this thing gets lifted. So it's either force parallel times the length, or it's the weight times the height. Now, here's the deal. When I multiply that weight by however high it gets lifted, what am I finding? Work, which is going to change what type of energy? Gravitational or kinetic energy?
Gravitational potential.
Yeah, you don't change up, right? You don't change your gravitational potential energy. Now, power is work divided by time. So you know your power, because that's a 300-watt motor. So you know this number. You can find the work by taking F and G times your height. The only thing you don't know is time. Okay? Anything else? Once, twice, sold. Shut that down. Okay. Now, I'm going to go through a whole bunch of math that you don't have to worry about. Okay? Do not write down anything until I basically tell you to. So, when you have collisions, there's two things that are always involved, momentum and energy. So you have energy because you have two things that are moving, hence you have kinetic energy. If they weren't moving, guess what? They wouldn't collide. Pretty simple. You also have to worry about momentum. So in a perfectly elastic collision, okay, and you would have to be specifically told it's a perfectly elastic collision, you conserve two things. You conserve momentum and you conserve mechanical energy. Okay? Mechanical energy means like kinetic energy. Okay? So in other words, in the collision, you're not losing any energy at all to sound, to thermal energy, to make anything vibrate. You're not losing any energy to, like, deform the metal itself. So this is an absolute idealized situation. And typically this only happens when you have like an idealized situation, like you have like two protons on an atomic level that would collide, okay? Because anytime you have like two cars that are going to run into each other, it's never a perfectly elastic collision because you're going to deform the metal and there's going to be brakes involved and there's going to be screeching of metal and all this other stuff. So unless you're specifically told it's a perfectly elastic collision, odds are it's not. Now, so you can only conserve mechanical energy if basically you don't lose that energy to something else. So the odd thing about energy is that energy can take on so many different forms. You can have thermal energy, you can have energy in bending metal. Okay, you can store energy in the collision by collapsing a spring. Okay, so there's a whole bunch of different ways you can store energy. Momentum, however, is a one-trick pony. Okay, momentum is just momentum. That's it. So in collisions, you will always conserve momentum, but you will only conserve mechanical energy if you are specifically told it's a perfectly elastic collision. So listen to me. Momentum is always conserved. There is no exceptions whatsoever. You only conserve pure mechanical energy if it's a perfectly elastic collision. Okay? Now, energy is also always conserved, but energy takes on these weird forms of thermal energy and sound and all this other stuff. Okay, so I'm going to go through a whole process that I will never ask you to do. Okay, so don't flip out and go, oh my God, we're going to have to do this whole test. No, don't even write it down. I'm just kind of showing you where you're going to end up. Okay, that's all I'm going to do. So we're going to deal with two things. We're going to deal with energy first, and eventually we're going to deal with momentum. So here's the short version. You're going to have two things. You're going to have a target, and you're going to have a bullet. Okay? So you're going to have a bullet, boom, there's a target. Target's going to be at rest, bullet's going to be moving in, boom, here you go, we're off to the races. So basically what we're saying here is that all of this kinetic energy before is going to equal the sum of the kinetic energies after. So this is why this gets real complicated. Because so then you've got 1/2, that was a horrible 1/2. 1/2 mass velocity of the target squared plus 1/2 mass velocity of the bullet squared equals 1/2 mass of the target times the new velocity of the target squared plus 1/2 mass new velocity of the bullet squared. Okay? So you've got all of this stuff to worry about. So here's the deal. This gets simplified rather quickly. Because right away, what can you get rid of? Mass or 1/2? 1/2, right? So all the 1/2s go away because I can multiply everything. I can multiply both sides of the equation by 2 and poof, it's gone. Now, here's what I want to do. I want to take and combine all the targets on one side and all the bullets on the other. So over here, and like I said, don't write this down, okay? Yeah, I won't ever expect you to do this. I'm just kind of showing you. So this is mass of the bullet times the velocity of the bullet squared minus the mass of the bullet times the new velocity of the bullet squared. Okay, so all I did was take this and move this over here. Okay, that's all I did. And then I'm going to take this target and I'm going to move that over there. So this is going to be the mass of the target times the new velocity of the target squared minus the mass of the target times the original velocity of the target squared. Go with this. Okay? All we did was just arrange this a little bit. Now, what can I do to make this a little bit simpler? What's common to both of these terms? Mass of the bullet, and I can do the same thing over here. I can pull out the mass of the target. So, I can have the mass of the bullet times the velocity of the bullet squared minus the new velocity of the bullet squared, and then I'm going to do the same thing over here. Mass of the target times the new velocity of the target squared minus the velocity of the target. Okay, not a big deal. Now, I want you to flash back to Algebra 1 for just a second. I said, all right, class, I want you to factor x squared minus 16. What would you get?
X minus 4, x plus 4.
X plus 4 and
X minus 4.
x minus 4, right? If you do that because it's the difference of
Perfect squares.
squares. Is this the difference of two squares?
Yeah.
Yeah, it is, right? So I can sit here and go, okay, well I can write this as the mass of the bullet times the velocity of the bullet plus the new velocity of the bullet times velocity of the bullet minus the new velocity of the bullet. Okay, so all I did was just the same thing that you did here. Okay, not a big deal. And then I'm going to do the same thing over here, mass of the target times the new velocity of the target plus the velocity of the target, and then the new velocity of the target minus the velocity of the target. Okay. Now, I'm just going to leave this here for now. I'm going to get back to this. Okay? So all I did was I rearranged everything, I got rid of the halves, and then I separated them out as the product of squares. So this is the energy side. Now, on the momentum side, how does every momentum problem start? Mary, how does every momentum problem start?
You would add the two initial momentums,
Yeah, so what are my two objects?
the bullet and
Target?
the target, yep.
Okay. So this is going to be the momentum of the bullet, the new momentum of the bullet plus the new momentum of the target. So this is going to be the mass of the bullet, velocity of the bullet plus the mass of the target, velocity of the target. This is why this takes forever, by the way, and this is why I don't have you guys do this. Okay? Now, I'm going to do the same thing over here. Okay? I'm going to combine my bullets, and then I'm going to factor out a bullet. So I'm going to have the mass of the bullet times the velocity of the bullet minus the new velocity of the bullet equals the mass of the target times the new velocity of the target minus the velocity of the target. So all I did was combine my terms and factor out a mass. Go with this. Okay? Everybody groovy. Now, because of the fact that these two things are going to be in equality, because momentum is conserved and energy is conserved, what I'm going to do is I'm going to basically divide both sides by all of this, okay? So I'm going to take what I had on the energy, and I'm going to divide that, all of that energy stuff by this, okay? So I'm going to come back over here, and this is going to divide this by, so I'm going to divide this by the mass of the bullet times the velocity of the bullet minus v prime of the bullet. And then I'm going to take all of this and divide this by the mass of the target times v prime of the target minus velocity of the target. Okay? So, what's going to go away?
Mass.
Yeah, so at this point, I'm going to lose the mass of the bullet. Okay? The mass of the target. What else is going to go away? This and this. So right now, here's what I've got. Velocity of the bullet plus v prime of the bullet equals the mass, velocity of the target plus the velocity of the target. Now, so here's what's important. Okay? So if it's a perfectly elastic collision, the sum of the velocities before and after have to be equal. So if you know what is happening over here, like let's say for example, you know that the original velocity of the bullet is 100 meters per second, whatever it is. And if you know the initial velocity of the target is a known value. By the way, let's make this simple. What do you think the initial velocity of the target is going to be most likely?
0.
0. So if this is 0, okay, that means that the two velocities of the bullets, guess what? They have to add up to whatever the new velocity of the target is. Okay? Cool with this. Now, this is just like phase 1. To actually get the full-blown equation, I've got to substitute this back into the kinetic energy equations and the momentum equations, and then do a whole other page of simplification, which I'm not going to do, mainly because y'all will be bored out of your mind and I'm tired of writing. But here's what's a simple little check. I just point this out, that if it's a perfectly elastic collisions, the velocities before have to add up to the velocities afterwards. So we'll revisit this idea in just a second. Now, here's what you actually need to know, okay, in terms of what's going to happen. Make sure it's right. Oh, seriously. Okay. So this is what you actually need to know, right? So here's, if you write down anything, this is what you need to write down. Now, on the test, if you need these specific equations, I will give them to you, okay? But you need these like to do today's assignment. There's going to be some questions on the assignment. These are on your equation sheet, so write these down so that you have them. Now, let's look at the big idea. So let's start with this new velocity of the target. Mass of the bullet times the velocity of the bullet. When I take the mass of the bullet times the velocity of the bullet, what am I finding? What's mass times velocity? What do you get? Momentum. So this is basically doubling the momentum of the bullet and dividing it by the sum of the masses. Okay? That's all this is. I could write this as 2 times momentum of the bullet divided by the sum of the masses. It would mean the exact same thing. Okay? Now, we're going to get back to this one. Okay? Now, what we're going to look at is 3 different scenarios that happen up here with the bullet and the target. Okay? 3 different scenarios. So scenario number 1 is the mass of the bullet equals the mass of the target. So in other words, let's say the bullet is moving at, has a mass of 5 grams and it hits a bullet, or excuse me, the bullet has a mass of 5 grams and it has a target that has a mass of 5 grams. So if those two numbers are the same, what becomes the new velocity of the bullet?
0.
0. Why?
Because
It just stops. Okay? So what's going to happen here is that if the mass of the bullet is the same as the mass of the target, basically the bullet's going to hit and it's going to completely stop. So then what's the target going to do?
it's going to go off at the speed of
It's going to it has to have the exact same momentum and the exact same energy as the
bullet.
bullet did. So it's going to stop. It's going to transfer all of its energy and all of its momentum into the target, and it's going to take off with the exact same speed and the exact same energy that the bullet had when it hit it. Okay? Absolute best case scenario. So if this is the same, that means that the new velocity of the target is going to equal the original velocity of the bullet. So if the bullet was coming in at 5 meters per second, the target's going to leave at 5 meters per second. Okay? Off to the races. So that's option number 1. Now, what if the bullet's mass is less than the mass of the target? You're on step 3. Let's start with step 1. If the mass of the bullet is less than the mass of the target, okay, what's going to be the sign of this?
Negative.
Negative. So if I take a negative delta mass, multiply that by a positive velocity and divide it by the sum of the masses, what's going to be the sign of the new velocity of the bullet?
Negative.
So what is that physically going to mean? It's going to hit and it's going to bounce back. Okay? So if the bullet is less than the mass of the target, it's going to come in, hit it, and it's going to bounce back. So if the... Oh, come on. So the second option, is the mass of the bullet is less than the mass of the target. That means that the new velocity of the target, or of the bullet, is going to equal a negative number, which means that it's going to bounce back. Okay? Now, if this happens, let's talk about what's going to happen with the target. Is there any way that I can get the target's velocity after the collision to be a negative number? Assuming that the bullet comes in with a positive velocity. Assuming that the bullet comes in with a positive velocity, is there any way the target velocity could be a negative number?
No.
No, because you've got everything that's here that is positive. Now, here's the reason physically why it couldn't happen. Okay? Because if you say, oh, the new velocity of the target is a negative number, so here's what you're physically saying is happening, is that you have a target that's at rest.
Moving towards you.
It's going to get hit with a bullet, and then after that, the target's going to go in that direction.
Maybe it's jet thrusters. You shoot a deer.
No. These deer collisions aren't perfectly elastic. Okay? I'm just saying, if it's a perfectly elastic collision, and this is a huge if it's a perfectly elastic collision, there's no way the target's going to be going in the opposite direction that the bullet came from. Okay. Now, what if this thing actually worked? Now, here's your third scenario. What if the mass of the bullet is bigger than the mass of the target?
Mass of the bullet's going to keep on moving, right?
Well, if this is the case, you're going to have a positive number up here, multiplied by another positive, divided by another positive. So what does that mean in terms of the sign of the the velocity of the bullet?
Positive.
Positive. So if the bullet's a lot bigger, he's going to hit it, and then it's going to keep going. Now, do you think it's going to slow down, though, after that collision?
A little bit.
Yeah, it's going to slow down some, because it's got to transfer some energy and momentum over to the block. Hunter?
I'm a little confused by, most of the time, if you shoot something, the mass is going to be bigger than the bullet, right?
Yes.
But if the mass of the bullet's smaller, then it bounces off, is what you're saying.
If you have a perfectly, this is a huge caveat, if it's a perfectly elastic collision, okay?
So I was going to say, if I shoot a person, it's not going to bounce off.
Okay, well,
What's an
Shoot me
example
at
of a perfectly
my
elastic?
The person's mass is going
okay, so come back here. Now, yeah, you'll see if they combine masses, it cannot be a perfectly elastic collision. It only works if they don't stick together.
So this like almost isn't like a natural like
Yeah,
okay.
like subatomic particles, like protons.
You don't hold the camera? Dang it. You get to watch me play
You're always
with
going to
that.
be that kid.
Child at heart.
Really.
Yeah, I'm gonna notice now. I'm sorry.
No, I pretty much bought into that pretty early on.
Personally,
Really?
Yeah, we watch lunch and encore.
I don't,
You're even in the same encore?
and we'll hang out on the weekend sometimes.
Yeah, that's true.
All right. Okay. So let's say that here's the bullet and here's the target. Okay? Okay. So assuming that these masses are the same and in a completely idealized situation, this should come in, if the masses are identical and it's a completely idealized situation, what should happen after the collision?
Bullet stops and the target moves.
Yeah, so this should come in with a certain amount of mechanical energy and a certain amount of momentum. So this should come in, hit it. This ideally would completely stop, and this would just keep going. And so that you can, to a certain extent, that's what happens. You're here, boom. It transfers all of that momentum and all of that energy over to here. This thing stops, it's gone, it offloads all of that through the plunger over to here. Okay, so that's an absolute best case scenario. Now, let's say that we're going to make the mass of the bullet, or of the target, really, really big. So I've got a really, really, really big target and a relatively small bullet. So now, if you look at what happens, mathematically, so I've got, in this case, a bullet that's going to be really, really, really big, and a target, no, small target. Small target,
Big target,
big
small
target.
bullet.
Big target, small bullet. So if I've got a big target with a small bullet, when I subtract this, what should happen? Negative number, which means the bullet should bounce back. So if we do this, comes in, okay? And that bounces back in that opposite direction. So there's no way, though, that after that, that this could go in that direction.
So is that target ideally supposed to not move?
No, no, no. No, the target always has to move.
Oh, okay.
There is no way the target
No,
can
you're
be
right.
at rest
Yeah.
after the collision.
That makes sense.
There is
Equal
absolutely,
opposite, right?
even then,
Okay.
it could have equal and opposite velocities, but there's no way that it could remain at rest. Because if you look at that mathematically, you're taking the momentum of the bullet, which is a positive number, multiplying that by 2 and dividing it by the sum of the masses. So it is impossible for the target to remain at rest. And it is impossible for it to go in the opposite direction the bullet was going. Now, if I take a really, really, really big bullet and hit a small target, then what should happen?
They'll both go that way.
Which direction?
Direction of the bullet.
Yeah. So if I have a really, really, really big target, bullet, hitting this, okay? I'm going to come in here. Now, an interesting thing happens. As it rolls, okay, what happens to the distance between them?
It's gonna
It's
be,
greater.
It increases. Why?
because velocity is smaller of the bullet,
Yes. And this is going
faster.
faster. So if you have a situation like this, then it's going to hit, boom, and this is actually going to increase that distance. So there's no way that they can have like the same velocities. Either it's going to stop and the other one's going to transfer it over. Something's got to change with those velocities based upon the masses. Now, let's look at this situation. So if I take it this way and push them, okay? So they did the California thing, right? So this is something that Hunter asked about. So if this happens, where they hit and they move off together, could this be a perfectly elastic collision? Why not?
Because you said so.
Well, I know I said so, but why did I say so?
Because their velocity.
Because the mass.
What'd you say?
Their velocity would be the same.
Yes. Look at what happens. If they move off together, what do they share? They share the same velocity. Okay? So there's no point in doing that calculation. That calculation allows you to calculate the two different things after the collision. If they hit and they move off together, they have the exact same velocity. So anytime you have a situation where two objects hit and move off together, there is no way it's a perfectly elastic collision because they merge together. You're always going to lose energy in making those things stick together. Okay? Got that? Okay, back we go. Here.
They can see everything from my perspective.
Oh, yeah.
Yeah, I sure wish you hadn't broken it.
Yesterday? No. I took so many photos.
What he
did?
just computer science. Is it a bad idea?
Grand Theft Auto, but you're a doctor. Like in a hospital.
Max likes this idea.
Go around the hospital and kill people with hospital.
Without getting caught.
Do I get to steal their organs?
Huh?
Do I
You
get
can, and you can sell them black market.
Dude, one of the quests has to be getting back Mr. Birdcamp's skull.
Making up a video game right now.
Just
Where you're a
spitball.
doctor in
Like
a
a doctor
hospital
serial
and
killer.
you're a doctor in a hospital and you steal people's organs to sell them on the black market, and one of the quests is to steal your gallbladder back.
What a greedy doctor. They get paid so much money.
He's donating the money from the organs to the poor. He's donating it to the people that he stole it from.
God,
What a good guy.
what an awful Robin Hood twist. What a goober. What a goofy. I don't think this is a situation where you use the word goober to describe this person.
Oh, I think it is. What a goofy goober.
You guys, you're not going to go to the game channel?
Probably will.
You will?
Yeah, probably.
Cool.
As long as you're not kidding you guys. Bring this to the command. Josh will be there, so just be here. So,
Okay,
will it be anywhere? Just there.
are we going?
Yeah, we're going.
Oh,
We've been
Yeah,
going for a while.
they heard about the. We haven't stopped since we were back there.
okay. All right, so great. Fourth block yesterday offered to make me a new gallbladder out of Play-Doh.
I'm an animal with Play-Doh. I
What
did
does
that
he
in
even
anatomy. You had to like make
Oh,
lines on it
it's
and
like
everything.
a kind of like
Bro.
You know, a bubble like that.
Ironically, that's where the Plato came from, was it magna? Okay. All right.
And there's
So
this
I'm
big
just gonna,
tube
we're
goes
just gonna
down
work through this to make sure that it all works, okay?
There's also a tube that goes up like this.
So you got a 3 kilogram bullet, moves at 4 meters per second, collides with a 1 kilogram target that's at rest. So I've got a bigger bullet colliding with a smaller target. So this could be a situation like, especially like in atomic physics, where you have a massive proton that might run into like an electron, or, you know, especially if you have like 2 ionized particles, okay, where one's going to be really big and the other one's going to be really small. So all I'm doing is finding the new velocity of the bullet. So all I did was take the difference between the masses. All I'm using is that formula. This isn't anything complex. So I'm taking 3 kilograms minus 1 kilogram, multiplying that by the original velocity of the bullet, and dividing by the sum of the masses. Well, that's pretty simple because the 4's cancel out. I take 3 minus 1, I get 2 meters per second. So what did the bullet do after the collision? Speed up or slow down?
Slow down.
It had to slow down because it had to offload some of that momentum and energy. Okay? That had to get offloaded. Okay. 2 meters per second. Now to get the new velocity of the target, again, when I take 3 kilograms times 4 meters per second, what am I finding here?
Momentum.
Yeah, this is just the momentum of the bullet. I'm multiplying it by 2, I'm dividing it by the sum of the masses. So the 4's cancel out, I take 2 times 3, I get 6 meters per second. Okay? We're good. Now, remember this. So we got 4, 2, and 6. So one of the things that you can check to see if this is reasonable, if you go back to where we ended up here, we said that when we add together the velocities before and after, the two sides should be equal. So we said the velocity of the bullet was 4, right? The new velocity of the bullet was 2. The new velocity of the bullet, the target was 6 meters per second, and the the target itself was at rest. So just by looking at this, I'm thinking, okay, we're cool. That's going to satisfy that initial set of conditions where the velocities are going to add up to be the same. Okay, got this. Now, let's actually see if momentum and energy are actually conserved. What are you going to deal with first, energy or momentum? Shai, pick one. Momentum, energy.
Energy.
Okay, that's the more difficult one. You chose wisely. Okay, so we're going to deal with energy. So I've got the kinetic energy of the bullet plus the kinetic energy of the target equals the new kinetic energy of the bullet plus the new kinetic energy of the target. So what's the initial kinetic energy of the target?
0.
0. Okay, don't have to worry about that. So this is going to be 1/2 my mass, which is, what was that, 3 kilograms? Yeah, 3 kilograms. And that was moving at 4 meters per second. That's going to get squared. So that's 24 joules. Okay? So this is going to be 1/2. What was the new velocity of the bullet? 2?
Yep.
That's going to get squared, and then add that to 1/2 the mass of the target, which is 1 kilogram, but that's moving at 6 meters per second. That's going to get squared. So six joules, and this is 36. 18. So 6 plus 18 gets me 24. Okay? So energy is conserved. So I add these together, boom, here we go over here. Now, realistically, which side do you think is, in a real collision, which side do you think in terms of pure energy of motion is bigger than the other one in terms of a collision? The before side or the after side?
Before.
Yeah, because it would be cool. If this side was bigger, in other words, if you had more mechanical energy after you had like a car crash. Number one, car crashes would be much more violent. Number two, we would have the world's energy crisis solved. Because if you had collisions and you ended up with more energy than what you started with,
You
ooh,
just make collisions on purpose.
yeah, we'll have a lot of collisions. Boom, we'll hook it up to a generator and we can make toast at the end of the day, and here we go. Yeah, we can make a lot of toast. Okay,
Dickens toast is unethical.
so what else has to be conserved?
Dickens toast is unethical.
Yeah.
Momentum.
It's just spiky.
So then I can go, okay, momentum of the bullet plus momentum of the target
Only eat
equals the
raw
new momentum
toast.
of the bullet plus the new momentum of the target. Target's at rest. This was
Cook it again.
3 kilograms moving at 4 meters per second.
Get it double
This
dip.
was 3 kilograms moving at 2 meters per second. And that was 1 kilogram moving at 6 meters per second. This is 12 meters seconds, that's 6 meters seconds. Voila, momentum and energy are conserved. Now, as we go through and look at different scenarios, here's what's always true. Momentum is always conserved because momentum is just a one-trick pony, okay? I can't have like, oh, momentum due to thermal energy or stuff like that, okay? Momentum is momentum. So no matter what, you always start with momentum being conserved. You can only conserve pure mechanical energy if you are explicitly told, I mean explicitly told, that it is a perfectly elastic collision. Because typically what you're going to have to do, like for example, you had the situation where with the carts, let me start over. And you had the carts and you had one cart that was like this and you had the other cart and they hit and then they moved off together, okay? So if you were to find the difference in the energies here, you'd have to find the kinetic energy of this by itself, and then you'd have to find the kinetic energy of the two masses after they move off. And in what you'll see, and it varies depending upon like the types of material and stuff like that, but typically when you have a collision where things move off together, because of the fact that it's velocity squared, you typically lose about 50% of your energy in a collision where things stick together and move off, okay? So, and what, again, you'd find this kinetic energy of itself, you'd find the combined mass is kinetic energy, and when you subtract the two, you'll see that you actually lose a lot of that energy in a collision, okay? All right. Now, speaking of momentum, so if I take yonder balloon and I blow it up, looks like a gallbladder. So I've heard. Okay, now I let go of the balloon. Is the balloon going to accelerate?
Yes.
So what does that mean?
There's a force.
There has to be a
Force.
force. There's going to be some kinetic energy involved. Is the momentum of the balloon going to change?
Yes,
Yeah.
because
Yeah.
the velocity
Yes.
is going to change.
Zero.
Because right now it has no momentum, right? If I let go of it and it goes flying off, guess what?
It's going to
It's
have
going to have momentum. So here's the story with momentum. So, there it is. If you look at change in momentum, right now, here's how you all are used to looking at change in momentum. You're used to looking at it as mass times a change in velocity, okay? So in your day-to-day lives, this is how you experience change in momentum. You press down on your gas pedal, right? You hit the gas, and you go, wow, I want to change the velocity of the car. I'm going to apply a force over a certain period of time, and here's the mass of the car, and the mass of the car is a constant, and I'm going to change the velocity. And then I can get clever and go, oh, well, that force equals mass times change in velocity over time, right? And change in velocity over time is nothing but acceleration, oh, this is just F equals ma, kind of repackaged. Oh, okay, that's kind of cool. So in your daily lives, this is what you focus on. You focus on mass staying constant and this force causing a change in velocity per unit of time. Up to this point in time, this is how you've experienced momentum. Now, but if you look at what's going to happen with the balloon, when I let go of the balloon, what's going to happen to the mass of the balloon?
It's gonna go down.
It's going to change. It's going to increase or decrease. Decrease, because I'm expelling the oxygen and nitrogen molecules out one end. So this is like a rocket, okay? Like a rocket. It's the same idea. So if you're talking about rockets, change in momentum still equals force times time. The rocket engines, we shift that a little bit because we change the location of the delta V. So rockets work by kicking out gas at a constant velocity, but you're changing the mass because you're consuming fuel. So this on a rocket becomes change in mass times the constant velocity. So when I let go of this thing, hold on. Oh, hold on, it's gone.
Gallbladder.
Let me down again. Okay?
Hello.
Okay? That was actually good. So what happened as soon as I let go of it, clearly there was a force acting on the rocket, or the balloon in this case, because of the fact that it went flying across. Yeah, don't touch my gallbladder. Back off. Okay. So here's what's important, is that if I divide this by time, then this force becomes a change in mass times velocity over time. So here's what I want you to see in terms of the difference. This one is a change in velocity per unit of time with a constant mass. This is a change in mass per unit of time multiplied by a constant velocity. So if you want a rocket engine to provide a lot of force, what do you want to have happen here? You want a big change in mass per unit of time or a small change in mass per unit of time? You want a big force.
Big. Big.
You want a big change in mass per unit of time. This is why rocket engines are huge, so that they can consume a lot of fuel and burn that fuel up. What about the velocity? You want a big force. What do you know about your gases when they come out?
They gotta be going fast.
You want them hauling the mail. So this is why rocket engines are huge and they burn hot, because hot gases have more velocities than cold gases do. So cold engines small cold engines on rockets don't work very well, okay? Because you're not burning much fuel and the gases aren't expelled very quickly. So imagine that I could take that balloon, right before I let go of it, I heated up the gas inside of it. Instead of like room temperature of about 20 degrees Celsius, I warm it up to about 100 degrees Celsius. What do you think is going to happen to the velocity of that balloon when it takes off?
It's gonna be a bit faster.
Yeah, because it's going to create more force because the particles coming out are going to be moving at a much greater velocity than if it's at room temperature. So, if you want a big force, you want a big change in mass per unit of time multiplied by a high velocity. So if you look at like the solid rocket boosters on the space shuttle, those consume about 2,000 kilograms per second, which is like about 4 small cars per second. And the gases are kicked out at about 400 liters per second. So those things are burning through a lot of fuel and expelling that gas very, very quickly, and that's producing a big amount of force that's going to act on the system. Got that. Now, speaking of mass, about couple odds main things to cover. One is what we call center of mass. So there are a couple of different ways you can look at center of mass. So let's say that I take this meter stick, and these are just a couple of pieces of round metal. And I'm going to start this on each end. I'm going to bring the metal together. So where do you think the pieces of metal are going to meet?
Probably the middle.
Maybe in the middle? Okay. And oddly enough, they meet right at the 50 centimeter mark. So, so what that represents, the center of mass, is the one point where you can basically balance anything. Now, what if, and I'm going to do this again, I'm going to start with this one here at the 30, and I'm going to start this one way out here on the end, and I'm going to move them together. Now where are they going to meet?
50.
Farther to
I'm gonna go-
your right side.
50.
They're
I'm
gonna
gonna
be
go
at
with
50.
middle.
If you move them at the same speed?
I'm going to move it, I want to move them at the same
70,
speed.
like the 50 middle.
Well, you moved the other one later.
Right.
Well, we pushed it with the same force. It just wouldn't move until
This is huge.
it's here.
Human error.
That had, the right one had to have been going fast.
Okay, hold on.
Uh-oh.
Stop.
It's not.
Okay. Now, Mother Nature is lazy, right?
Correct.
Okay? So, if I put this at 30, which one do you think has more friction acting on it? The aluminum rod or the iron rod?
Alright.
Has more friction.
Okay.
Oh, you get to the left.
Because look, this is close. This one's close to the center of mass, right?
Yes.
This one's way out here on the end. So this one isn't like supporting as much. So when I begin to move these together, nature takes the path of least resistance. So when I slide these together, this one's going to slide easier because of the fact that it's not supporting as much weight. There's less force normal, so there's less force friction. So then when I slide these together, eventually they do start to move just like they did, and you end up into that center of mass. Okay, so no matter where I start, I'm still going to end up in that center of mass. Now, I'm going to change it. Okay? So I'm going to put a 200 gram mass at the 30 centimeter mark. Okay? I'm going to do the same thing. Put one out here. And put this one over here. Now where are they going to meet?
Closer to the right.
They're gonna meet right underneath.
Yeah, right underneath.
Right underneath.
No, no, they're gonna meet slightly to the left, to our left of it.
Yeah, go on. Center.
Okay? Now, why did it meet directly underneath the 200 grams?
It's out here.
Yeah. Is there still some of the meter stick over here on this side? Ow. Over here on that side.
Dang it.
All right, Bree. Take it over, Bree. Okay, so was what?
Oh, this is funny.
So there will still be some mass over here, right?
Yeah.
Okay, so it isn't like this has no mass. So it met just a little bit to the right of that because there was still some mass out here that was creating this torque. So this is important in terms of like if you're talking about center of mass. You're trying to send, the InSight Mars to Mars on that probe. You have to know where the center of mass is because that impacts your entry angle. Okay, the Apollo missions when they were coming back from the moon, they had to compensate even for where the moon rocks were in the ship because where their center of mass would affect how they came in, the angle that they had when they entered the Earth's atmosphere. So, mathematically, it's a simple idea. It's somewhat similar to torque, but we're leaving out the force aspect of it. We're only dealing with the mass aspect of it. So imagine this. Let's say that I've got a rod of negligible mass. Okay, And 0.2 meters from the end, I've got a 1 kilogram mass sitting here. And then, say, 0.4 meters from the end, I've got a 5 kilogram mass. So, here's the deal. So here's the end of the rod. That's 0.2 meters. I've got a 1 kilogram mass sitting here. Out here, I've got a 5 kilogram mass that's 0.4 meters from the end. So before we do any calculations at all, where do you think the center of mass is going to be between? Between the 1 kilogram and the, okay, closer to the 5, closer to the 1.
Closer to the 1.
Closer to the 5, because that's where you're going to have more mass. So what we're trying to find is the single point where we can make this thing balance. That's what we're after. So, mathematically it's simple, but here's what you want to do. You want to measure everything from one end, okay? Now, if you're clever, even if you have like, even if I had like a half a kilogram mass sitting here on the very end, if you're clever, what are you going to let the initial position of this end be? 0. So even if you have a mass here, that can still have a position of 0. And that's what we're going to do on your assignment. You're going to have like the Earth and the Moon. You're going to try and find the center of mass of the Earth and the Moon. If you're clever, you're going to go, oh, hey, I'm going to let the Earth have an initial position of 0. Takes it out of the equation. You don't have to deal with it. Okay, so here's what we'll do. We'll use this formula. We're going to take that mass, 1 kilogram, multiply that by 0.2 meters, and then we're going to add that to the second mass, which is 5 kilograms, and we'll multiply that by that distance, which is 0.4 meters. And then I'm going to divide that by the total sum of the masses, which is 6 kilograms. So somebody take 5 times 0.4, add that to 0.2, and then divide all of that by 6.
0.367.
So 0.37, right? Which would put us about right here. Okay? So what that means is if you had a knife's edge and you put that knife's edge right there, that's where everything would balance. Okay? Right at that point. Would it be possible for this center of mass to end up outside of that last mass? Could that happen? No, because if guarantee you, if you try and balance it outside of here, what's it going to do? Doink. Okay, and it can't be over here because it's going to go doink. So basically, when you find that center of mass, that's at one location. So this is pretty important. Like, if let's say you want to be a pilot, okay. So here's a little Cessna, okay, fixed wing. Right, boom.
Oh, we should do the circus people.
Huh?
The circus people. On the who stand on the, you know.
The ball?
Yeah.
Rope?
You stand on like the
So
stake
on
that
the
stands
wing?
up and you have to like.
Tightrope won't be, right?
That's an impressive airplane, I'm just gonna throw it out there.
I'm not done yet, but yeah. So, actually, we'll change it up a little bit.
Oh, yeah.
Oh,
Yes, sir.
that's an impressive airplane. Okay, now let's say you're landing your little Cessna airplane, right? And it's got the tricycle landing gear. When this thing lands, assuming that the propeller isn't digging into the ground, when this thing lands, where do you want the center of mass to be? Behind this wheel, back over here, or in front of this wheel? Probably behind. So you want the center of mass to be back here.
I don't know.
If the center of mass is back here, when you land, what's it going to do?
You're gonna do a sweet wheelie.
Yeah, so you want the center of mass to be.
If you're smart, you just put pontoons on it and land it on a lake.
Not. Okay, guess what? The center of mass, if it was back there, you'd go doink. Okay. So you want that center of mass to be somewhere forward of that landing gear. Because if it's not, when you land, bad things are going to happen. Now, but if it's like a one that's a tail dragger, where your wheel is back here and you don't have the front landing gear, then where do you want the center of mass?
Back.
Then you want it towards the back. Okay? So depending upon how your landing gear is situated, that's going to alter where that center of mass needs to be located. And this is one of the main things that pilots have to worry about. I don't care how big a plane they're flying. That's one of the things that they worry about is where is that luggage being stored and how are we going to adjust that center of mass. Good with that? Okay. Now, let's talk rotational kinetic energy. Okay? So if I take this wheel, what do I need to do to make the wheel spin? I have to apply a force, right, over a distance, right? Now, if I apply just a little bit of torque over a little bit of distance, I don't do much work. If I apply a bigger force over a bigger distance, guess what? I do more work. So, do you think on rotating objects, do you think work is related to a change in rotational kinetic energy?
Probably.
Probably so. Because guess what? If I don't do any work to the wheel, what does the wheel not do?
Spin.
It doesn't spin. Or if it's spinning, it doesn't
Stop.
Oh, it's equal?
Now, so if I want to make this thing spin, right? So rotational kinetic energy is 1/2 I omega squared, right? Now, what's I? Quick refresher.
Moment of inertia.
Moment of inertia. This is your butt, which is how fast you spin. Now, what are the units for any moment of inertia? Well, what's the general form, what's the simplest form of any moment of inertia calculation?
It's
mr squared. But what's the only situation where you can use mr squared?
When you have a thin hoop, right?
Point mass or
Thin.
thin hoop. Otherwise, you can't use this, okay? Because you're going to have to revisit that on today's assignment. So when I multiply mass times radius squared, I get units of perhaps kilograms meters squared.
Yeah,
Sounds good to me.
Radical concept.
sounds about right.
Seems good. Now, what units are butt measured in? But that's going to get squared, so we get rad squared, which we don't worry about, over.
second squared.
So we get kilograms meters squared over second squared, otherwise known as, somebody said it, joules, right? Oh, Newton meters, same thing, right? So this is going to be in joules. So the work that I do on the wheel is going to change my rotational kinetic energy. Okay, that's what I'm going to do. I'm going to do work. I'm going to change that amount of rotational kinetic energy. So if it's at rest, and then I know how much kinetic energy it has later, that's how much work that I do. What does power equal?
Watts.
Now that's what it's measured in.
Work over time.
Work over time.
It's work over time. Guess what? I can also express that as change in kinetic energy over time, or change in gravitational potential energy over time, or change in kinetic energy over time. So if I take this wheel and give it just a little bit of a spin, I don't do much work because I didn't change the kinetic energy very much. Now, if I apply a lot of torque over a large distance, then I really change that because I've done more work and I've done more to change the kinetic energy. If I stop it, am I doing work?
Yes.
Yeah, because I am decreasing that kinetic energy. Got it?
You're
Good?
also doing work because you're making friction with your hand, the heat and everything.
Yes.
That's pretty good.
Okay. Mad Max, shut that down.
we're only like a minute and 15 seconds from an hour.
Huh?
We're only like a minute and 15 seconds
Oh,
from an hour.
okay.
What is that?
Yo, Matt,
What?
what equation is he talking about on the 7th?
1/2 kx squared.
What do I find K, the function?
Yeah, you found it when you found the slope.
Oh yeah, I forgot about that.
Great. Can you do me a favor and email me that program that you used, like when you were taking notes? Yeah. I just need the name of that app.
All right, there's several of them, but I can send you a few of them.
Okay.
It's all reference. Burkamp doesn't have on an iPad grading system?
Oh, I don't know. I'm intrigued. How about that?
So wait, are you saying not only would I see your furious writing, I'd also hear your angry voice whenever I messed up?
That is.
Oh, no. Oh, no.
There could be voice memos.
No, no, no.
You could put
No.
voice memos.
But I just
No, it's bad enough what I write. It's not going to be what's going to happen when I'm talking.
Is it not
Okay.
school appropriate?
No.
Oh my gosh, Burkamp, you cuss us out at your house.
Nope.
He does.
What do you mean in person?
Wait, remind me your email.
sburkamp@usd266.com. Now, start that up.
Okay.
Okay, now, this is kind of like a review for your final, in the sense that I've thrown some old stuff into this. Problem number 1 is an old school momentum problem. Okay? You got a boat and Timmy throwing a rock. Momentum before equals the momentum after. So number 1 is just old school momentum. Okay? Old school momentum. Number 2, you determine the force exerted on a rocket. Okay? You've got a rate of 1,500 kilograms per second, a speed of 400. You're going to try and find the force. So on number 2, you're going to go to this idea here, where the force is going to equal that change in mass per unit of time times the velocity. Okay? So on number 2, go with this idea. When you get to number 3, you got a dart, you're going to compress the spring. You got the spring constant. With what speed does the dart leave the gun? So number 3 is conservation of energy. You're going to have a spring and you're going to have kinetic energy. Set up the chart, find the sums. Okay? Figure out how much energy you had before, that has to equal the energy afterwards. When you get to number 4, solid cylinder, mass, tangential forces applied. Now, on number 4, remember that torque equals 2 things. What are the 2 things that torque equals? Equals what? Force times radius, and also equals I fish. Okay? So, now, you have a solid cylinder. You need to look up the moment of inertia of a solid cylinder. It is not mr squared, but it's on your sheet. You're going to use that to find that moment of inertia. When you get to number 5, I tell you it's a perfectly elastic collision. You're going to use the equations that we came up with to find the new velocity of the bullet and the new velocity of the target. When you get to number 10, okay, you've got the mass of the Earth and the mass of the Moon and how far apart they are, and you want to find the center mass of the Earth and the Moon. So on number 10, here's what I would recommend. Here's the Earth, here's the Moon. If you're clever, what are you going to let the initial position of the Moon be? Excuse me, of the Earth be?
0.
0. So let the initial position of the Earth be 0, and then you're going to know the position of the Moon from there. Now, you don't have to do it that way, but life's going to be easier if you do. Okay? All right, you're on your own. So,